Can you hear us?
Yes, sir.
Okay. Can you see the board?
Yes, sir.
Okay. So advanced quantum mechanics will start at 12:30. Although I set the timing at 12:20, we will start at 12:30. Okay.
Okay, sir.
Okay. It's recording is back.
So, what we have
Same.
did.
The exams. So far, at least nothing is almost.
But any time can come. We
No,
know.
that's good. I see what I Okay, so can you people see the board? Should I switch off this board light?
Yes, yes, ma'am.
Fine now? Okay. Alright, so last time I was giving you this, we were trying to discuss about physical applications of lenses. And in particular, I said that I will discuss in some detail application of this sensor analysis to track of the moment of inertia. Or actually, what's known as inertia tensor. So essentially, that means that you're considering a rigid body. So it's a rigid body with masses held at fixed positions, and then you're rotating that rigid body. So when you rotate the rigid body, then obviously you're going to get some angular momentum of that rigid body. And then the angular momentum, what we saw last time, can be expressed most generally in the following way. So I'll write this as a lag component equal to omega. Everything else is exactly like what we had earlier, where my MIG was defined in the following way. So if I imagine my rigid body to be a collection of n particles labeled by alpha and each with masses n alpha, then this MIG is defined as the sum of this IIG, and IIG alpha in turn is defined as or in other words, this I is a second rank tensor. So the alpha particle is a second rank tensor depending upon the positions or the components of the position vector xi, xt, and r. So it's like r squared. So most generally you can say it's like r squared delta ig minus xr. And since we've already established that this quantity is a second rank tensor, and all I've done is multiplied with the scalar. So this for each alpha particle, this is a second rank tensor. And then if you look at the total n, it's simply a summation of n such second rank tensors. You can say that this quantity is second rank, or again, emphasizing these are Cartesian tensors. And this is what we will call as our inertia tensor. But you can also see some other. So this is where I think I stopped last time. So let's examine a little bit more about properties of this tensor. Now here you can see IIJ alpha is the same as, because you can see if I exchange IJ indices, this get exchanged, but delta is in a symmetric tensor. So this is symmetric, and here I'm just multiplying x1, x. So for example, if you have IJ equal to 1 and 3. So it's like x1 alpha, x3 alpha, but x1 alpha times x3 alpha is the same as x3 alpha times x1 alpha. So you can see that it is symmetric under exchanging these two. Or in other words, for the alpha particle, this I is a symmetric tensor. So for each it is symmetric. I'm adding up a summation of, or I'm summing up over n such symmetric tensors. So therefore, what you can see is that this M is a symmetric tensor. So the inertial tensor is a symmetric second rank tensor. And further, you can also say, because these are real numbers, so it's a symmetric, it's a real symmetric second rank tensor. Alright. So now again, if you remember what we did earlier, so if you have a matrix now which is symmetric, so if I look at M dagger is nothing but M star transpose. So what this tells me is that this implies that your M transpose is the same as M because it is symmetric. So M dagger then is equal to M because M star is the same as M transpose, which is equal to M. So your M is therefore, so M implies that your M is Hermitian. So again, this implies that I have three real eigenvalues. This is what we did just the last time. I think I was showing you that I can have three. So again, this implies that I can have three real eigenvalues. I can only have real eigenvalues. And let us say that we label the eigenvalues as same. We will get 3 because it's a 3 by 3 tensor. So let the eigenvalues be lambda 1, lambda 2. Then in that case, what you can say is that if I diagonalize my M diagonal will be simply lambda 1, 0, 0, 0, 0, lambda 2. So now I can imagine that what I can do is starting from an M, which is most generally like this, I can go make a transformation. So you know that you can make a similarity transformation and go from this non-diagonal form to a diagonal form. So I can construct MDS, or I can write my M to be in this fashion by some similarity transformation. Where S is some similarity transformation. So now you can see that also you can check. Okay, the people have done this in MNP. How will you find out such a similarity transformation? That what is the similarity? Suppose I want explicitly, so S is some similarity transformation which diagonalizes how would you explicitly find this? That what is a similarity transformation? You have done this, right? This in your MNP class. How would you explicitly figure out what are the or what is this matrix, the transformation matrix? Nobody? Somebody please tell something. Okay, how would you find the eigenvalues? I mean, how would you diagonalize a matrix? Okay, let's forget about the transformation matrix. How would you find out, how would you diagonalize the matrix? I mean, how would you find out the diagonal that? I mean, how would you diagonalize the matrix?
First, we find the eigenvalues.
Yeah, okay. Correct. So once you know the eigenvalues, then those eigenvalues themselves form the eigenvalue. I mean, you can show that these are the diagonal elements, all the others will be off diagonal. Okay. Now, when you do this diagonalization procedure, or when you do the eigenvalue problem, you solve it like this, right? So you write n equal to lambda n, and these are your eigenvectors, the corresponding eigenvectors. So now, have I given you a hint about how to find out this S? The transformation matrix, it is going to diagonalize your n. Any idea? This is I mean, this is an exercise which you people do in your matrix. I mean, actually in matrix algebra when you studied matrix algebra. So I assume that you must have learned either both in your BSc class as well as in your first semester of MLB. Okay, let me give you a hint. Suppose I know the eigenvectors of this. From using those eigenvectors, can I figure out what is the transformation matrix S? Okay, if you people have not done this exercise, it's because it doesn't make much sense for me to go ahead if you don't. I mean, if these basic ideas are not known. So okay, since I'm not really getting a response from you people, exercise is that given a matrix n, given a Hermitian matrix, I mean, for explicitly, let's take some Hermitian matrix and take a 3 by 3 matrix. Because 2 by 2, okay, you can start with 2 by 2 also. So take 2 by 2 and 3 by 3 matrices. Assume that this is Hermitian. Now find out how to diagonalize that matrix. Then the next step is what is the transformation matrix or what is the similarity transformation. Explicitly find out what is the similarity transformation matrix S, which diagonalizes it. Okay. This is an exercise for you. In case
Eigenvectors are expressed in column of
exactly.
form.
Yeah, so only thing that's right. So you take the eigenvectors, place them as columns, or it depends on whether you place them as columns or rows. It depends on how you define this. And once you do that, that will give you a S. And here, see, for example, if I have these three values and if they are distinct, then I know those three eigenvectors must be orthogonal to one another. So, in fact, what you can show most generally is that this S is really an orthogonal, even if they are not distinct. What you can show is that your S or the diagonalizing matrix, the similarity transformation, is a orthogonal matrix. And because it's an orthogonal matrix, essentially what you're doing is you're transforming from some basis to another basis, to the eigenbasis basically, because in that eigenbasis, your M looks diagonal, and you're transforming to that by an orthogonal matrix, which is nothing but our rotation matrix. Or in other words, what you're doing is I'm taking a particular choices coordinate system, and then I'm going to this new system of axis, which essentially where the unit vectors are the eigenvectors, normalized eigenvectors of this matrix. And you can go from this to this by rotation transformation. So this S actually will turn out to be nothing but an orthogonal matrix. In case, I mean, those who have either forgotten, because most likely you have forgotten this, I would request you that you please go and refresh your memory with this and explicitly do this for some matrices. Okay. So if I've done this, so if I've gone to this new basis, so let's assume that these are my eigenvectors. So I've gone to this new basis. So instead of using U, I will write n e prime equal to lambda e prime. Now you can see that in this new basis, e1 prime, e2 prime, e3 prime, which are essentially the eigenvectors of this M, corresponding to the eigenvalues lambda 1, lambda 2, lambda 3, name is diagonal. So then in that case, your angular momentum simply will become so in this new basis, your Li prime will be simply equal to lambda I delta ij, and here there is no summation over alpha. So this axis, the E1 prime, E3 prime, E3 prime axis are called the principal axis. Okay. Of the inertial basis. So if you're basically then what this is saying is that if you're making a rotation about the principal axis, but about any one of the principal axis, then the angular momentum and the inertia tensor or the moment of inertia, because these diagonal elements, as I told you, are called the moments of inertia. And it's simply because in this particular basis, if you're in the new basis, lambda 1 will be simply equal to m alpha times r prime squared minus x prime 1 square x2 prime square. So it will become simply like x2 prime square plus x3 prime square. So okay, I'm writing down specifically. So in the new basis, it will become simply. So in this basis, your I prime ij alpha will be simply equal to I'll just write out each element. I1 multiplied in alpha times. That's what we will get for I1. Similarly, your I2 prime alpha will be. So only you will get diagonal elements, will be m alpha times. Because you see now if we put 2 here, I have 2 here, and I have 2 and 2, remove that one. So I'm simply going to get x1 prime alpha whole square plus x3 prime alpha whole square. But these are the components in the new basis. I3 prime alpha, and lambda 1 then will be simply the summation of this I11 prime alpha over all alphas. Lambda 2 will be the summation of this. Okay, and all other I prime alpha IG will be equal to 0 I0. And your lambda I is, so lambda 1 will be equal to summation over alpha. I write here I here, no summation of alpha. Okay, now looking at this definition, you can also say one more thing, that these eigenvalues must always be greater than or equal to 0, because this is simply nothing but sums of squares. So it also tells me that your lambda I must be always greater than or equal to 0. So they are not just real eigenvalues, but they are actually positive real eigenvalues, including 0. It could be positive 0. And so if, for example, if I now rotate, say for example, about the one axis, let's say I rotate about this one prime axis, then in that case I'm simply going to get lambda 1 times, and let's say I rotate by angular frequency omega 1. So I'm simply going to get my angular momentum to be aligned fully along 1 prime direction, and the value will be simply lambda 1 times omega 1. And you can see that this is nothing but a summation over this with x2 prime square plus x3 prime square. Now, what is x2 prime square plus x3 prime square? So if suppose your alpha particle was here. Okay. What is x2 prime? X2 prime is the component of the position of the alpha particle along the E2 prime direction. Similarly, your x3 prime is the component of the position of the alpha particle along the E3 prime direction. So if you look at x2 prime square plus x3 prime square, this is nothing but the perpendicular distance of the alpha particle from the E1 prime axis. Because you just imagine that this suppose is my E1 prime axis. Then if I look at some alpha particle position here, so this distance is nothing but, suppose think of this as the x-axis, then this is going to be plus x. And that is how you will understand the moment of inertia, in fact, that it is nothing but the product of mass times the perpendicular distance from the axis of rotation. So that's why, in fact, this is called as moments of inertia. And I should also mention that the off-diagonal elements are called as products of inertia. So the diagonal elements are known as moments of inertia. Off-diagonal elements of M are called as products of inertia. So if you are in the principal axis basis, then in that case your products of inertia identically equal to 0, only you will get these moments of inertia. These lambda 1, lambda 2, lambda 3 are also called the principal moments of inertia. In general, when you have the M matrix, then M11, M2, M22, and M33 are called the moments of inertia. And M12, all the off-diagonal elements are called as products of inertia. And if you go to the diagonal basis or the principal axis basis, then in that case, diagonal elements are called as the principal moments of inertia. Now we can also see from this that, okay, now examining this moment inertia is a little bit more, I'll tell you about this. Here I assume that they're all distinct, the lambdas are distinct, in which case you know that you're going to get 3 orthogonal eigenvectors, and we will choose these as E1 prime, E2 prime, E3, and they will form a mutually orthogonal set of coordinate axes. But suppose you are lambda 1, so let us assume that now they are not distinct eigenvalues. Okay, so now let lambda 1 and lambda 2 equal to lambda 3. That means I don't get 3 distinct eigenvalues, but I only have 2 distinct eigenvalues. So my matrix in diagonal is going to look like this. In this case, will I still be able to find my principal axis? So if you look at your eigenvalue equation, it's going to become equal to lambda E prime. So because lambda 1 is not equal to lambda 2 and lambda 1 not equal to lambda 2, then certainly I can say that the eigenvector corresponding to this and the eigenvectors corresponding to these must be orthogonal to 1. So let us say I get one eigenvector for, let's say that I get E1 prime is the eigenvector for corresponding to lambda 1. Now what about these two? Because now these are both are not distinct, they are the same. Is it possible for me to find some orthogonal set of eigenvectors? How will you find? Because now these two have become degenerate. No? Again, these are problems these are actually applications of what you have done in your MMP1. So it is still possible to do. What you do is, see, you have got E1 prime. Suppose I've got this E1 prime. Let's say that this is the eigenvector corresponding to lambda 1. Then you know that because lambda 2 is not the same as lambda 1, you know that the eigenvectors of these two must be orthogonal to this, the eigenvector of the corresponding to eigenvalue lambda 1. So it means that the eigenvectors for corresponding to lambda 2, the other two eigenvectors must lie in a plane which is normal to E1 prime. So find out what is a plane which is normal to E1 prime. And then what you can do is, you can take in that plane now, because it's a plane. That means it's a two-dimensional vector space. So then I can choose any two orthogonal vectors as my basis vectors. So even if they are two distinct, suppose you find that two of the eigenvalues are not distinct, it is still possible to find a mutually orthogonal set of three axes. But in this case, now what you can see is that suppose now, because the fact that you have, what it means is that, see, if I see, because what I told you is that you can choose, so if lambda 1 is not equal to lambda 2 equal to lambda 3, then choose eigenbasis in the following way, choose principal axis as you can choose as E1 prime and then E2 prime perpendicular to E1 prime. So choose E2 prime and E3 prime perpendicular to E1 prime and E2 prime perpendicular to E3. So they lie in the plane which is normal to E1 prime and they are mutually perpendicular. So again I can choose like this. But since all I'm getting from this eigenvalue considerations is that I can choose E2 prime and E3 prime to lie in the plane normal to E1 prime. It means that when I do a rotation about the E1 prime axis, my rigid body must remain symmetric with respect to the rotation. Because it is not going to tell me whether, because you see, I could, let's imagine like this. Suppose I have got the Z axis. Suppose this is my E1 prime Z. Okay? Then how I choose my X and Y axis is up to me. Because once I fix a Z axis, whether I choose this as X and whether I choose this as Y, or whether I choose this as X and whether I choose this as Y, it doesn't matter. All I have to choose is two vectors which lie in this XY plane and or in this plane which is normal to this Z axis or to this axis, and they must be mutually perpendicular. That's all I have. So whether I choose X like, so in the X axis I can choose like this, or rotate in, or in other words, any other two set of mutually perpendicular axes which are rotated about the Z axis still constitute a good eigenbasis in this case. So what this tells me then is that if you have two principal, or if you have two eigenvalues becoming the same, then it means that your rigid body has a rotation symmetry about the lambda 1, in this case about the lambda 1 axis or E1 prime axis. So it has one symmetry axis. Okay. So by looking at therefore the inertia tensor, I can tell you something about my rigid body itself. Because if it has a symmetry axis, then what it tells me is that I have a cylindrical geometry for my rigid body. It's a cylindrical geometry along, for example, the E1 prime axis. That's what it is. I could even ask one more question. Suppose I have all three are the same, then in that case, what do you expect? Suppose if lambda 1 equal to lambda 2 equal to lambda 3, then what are the principal axes? Can you say something about the rigid body in that case? See, because now in that case, it means your MD has simply become lambda 1 0 0 0 1 0 0 0 1. Lambda 1 equal to this equal to this. In that case, can you tell something about the symmetry of my rigid body? What do you expect?
Symmetric about all the principal axes.
Yeah. So how it okay? So how will you choose the principal axis now? So what is the form of this? This is written as this has become thing. Now, what is this matrix? Can we write this in some familiar form? 1 0 0 0.
Yeah, identity.
Yeah, it's identity, but I want to write it in the form of a tensor. So you can see that your M diagonal Ij is nothing but lambda times delta Ij. What kind of a tensor is delta Ij?
Isotropic.
It's an isotropic tensor. Very good. So therefore, can you tell me how should I choose my principal axis? Use this fact that it's isotropic. See, because it's isotropic, what is the meaning of isotropic?
Same in all directions.
It doesn't depend upon any particular direction. That means it is symmetric about all directions. So in that case, what it means is that I could choose any set of three mutually orthogonal directions as my principal axis. Because I need three axes because of three perpendicular axes because I know this is a vector space which is three-dimensional. But the fact that this becomes now an isotropic tensor tells me that I can choose the principal axis to be any set of three mutually perpendicular axes. Or in other words, what this is telling me is, or equivalently, what it's telling me is that the fact that I can write it as an isotropic tensor, that my rigid body is now rotationally symmetric or its spherical shape. Because it must be of a spherical geometry. Because if your rigid body is spherical geometry, then it doesn't matter which direction I'm seeing. It looks the same from all directions. So in fact, what this therefore tells you is also that now I can put the question the other way around, that if I tell you that my rigid body is spherical symmetry, then if I ask you what is the moment of inertia tensor for that, then immediately you can say that the answer should be obvious. Because you should immediately say that then I must get a spherically symmetric or an isotropic tensor. It's a second rank real symmetric tensor. It must be isotropic because of spherical symmetry. The only general second order spherically isotropic tensor is delta I, so therefore this is only the because it can be at plus multiplied by C. So I don't need to now explicitly do any calculations. So as I said, that what this tensor analysis does is it allows you to understand or to get the symmetry properties in a very neat and nice way. I mean, and it's very obvious. So for it, as I said, that if I know spherical symmetry, I just know the answer. If it's cylindrical symmetry, then also I know the answer. So I know that one of them will be different, the other two must be the same. So if I tell you the axis around which you have the cylindrical symmetry, then you can say that around that axis you get one answer which is different, the other two axes, the moments of inertia must be the same. Now let's consider one more case. So suppose I give you now, because we saw that these moments of inertia, because these are sums of squares, can be, the eigenvalues can be great. I mean, the lambda i's are greater than or equal to 0. Now let's assume that one of the eigenvalues becomes 0. What does that mean? Suppose one of the eigenvalues is 0. Oh, okay, look at the definitions. Okay, so because if it is 0, then what it means? What does it mean? Suppose one of these eigenvalues becomes 0. Let's say when can this become 0? If I have to have, and for simplicity, assume that we only have one particle or say two particles. When can it become 0? The eigenvalues.
At the origin.
Yeah, certainly. So I suppose I want lambda 1 to become 0. What will that imply? So there was somebody who was saying something. Please say. If lambda 1 must be 0, then what will that imply for? When can that happen? The lambda 1 is a summation of over all these I11 primes. I11 prime is this m alpha times this.
When the particle is on the x-axis.
When the particle is on the x-axis. Okay. That means it's not just one particle, all the particles must be on the x-axis. Right? Because only then your x2 prime alpha will be identically 0 for all alphas, and similarly x3 prime alpha will be identically equal to 0. Now all the particles are on the x-axis. or x prime axis actually here. What does that mean? What is the shape of your rigid body then?
One-dimensional,
It's a unit.
linear.
Yeah. So, if any of the lambdas are 0, if let's say a particular lambda is 0, then what it means is that implies that particles are collinearly arranged with respect to the and it's linear. With respect to EI prime axis. So it's really like a one-dimensional arrangement. Okay. And now you can see that if I rotate now about this EI prime axis, so I've got, imagine this is my body, think of this as just one dimension. If I rotate about this, I can't see any angular momentum along the x-axis, along this axis. And therefore what you will find is that then Li prime will be identically equal to 0. But the angular momentum about that axis will be 0. So lambda is 0. But you can also say it from a physical sense that if I have a one-dimensional thing, and this is something you must have learned in your quantum mechanics also, that if I have just one dimension, then I really can't, I mean, even if I rotate, I still simply will get the same arrangement. So, therefore, in that case, what you will find is that it essentially means that it's really arranged along that particular axis. Then any other two axes which are perpendicular to the x prime axis will be the principal axis. So I hope at least I will say one more thing now. So far I've talked about the angular momentum, but obviously now because you have this rotational frequency, the system will also have a kinetic energy. Now, how is the kinetic energy written for the system? Like in general, how is, if I have a collection of particles, what is the kinetic energy for that system? By definition, suppose I have a particle, what is the kinetic energy of a point particle?
Half mv square.
Half mv square. So if I have one particle, then I'm simply going to get half mv square. But your v is nothing but dr by dt. Okay. So I can write this as m dr by dt. But now I have a collection of n particles. So it's simply going to be this. My total kinetic energy for the system of n particles is simply going to be this. But what is we already have seen that this is nothing but equal to, so for the alpha particle this is going to be omega cross r alpha because we have got the z rotation. So I can write this therefore now as half sigma alpha is equal to 1 n m alpha omega cross r alpha. So I will use the fact that v alpha equal to omega cross r. With omega cross. Now we can see this such an expression we can very easily simplify. So this is a vector, you know, because I'm multiplying two vectors. This is another two multiplying. Sorry, I'm taking the cross product of two vectors here. Here also I'm taking the cross product of two vectors. So I'm going to get two vectors here, and then I'm taking the dot product of the vectors. But now you see I can simplify the algebra here considerably by using all the analysis we did. Now omega cross r, we can write it as, so this whole expression I can write it in the following way. As equal to half sigma alpha. See, this thing is nothing but omega cross r alpha I omega cross alpha. Because that's what this dot product. It's like A dot B. A dot B is nothing but AI BI. But here we simply have A dot A, so therefore I simply AI BI. But I know what is the ith component. This ith component, I can write it as epsilon IJP, omega G, R alpha, X alpha. And similarly here, I can write again the ith component in terms of epsilon I. And now because these are dummy indices, I should not use the same J and K here. I use two different dummy indices, omega N and X alpha. I use instead of N minus N here, so that you won't confuse with the mass. And then you have this M alpha here, then I have the summation. And the half factor here. So your kinetic energy simply becomes this. But now you can also use the fact that I have your epsilon IJK and epsilon IMN. So it's a contraction of these two Durganandini tensors over the index, first indices, and we already know the identity there. So I can write this as half alpha equal to n alpha. And if I use the contraction here, I get delta Jn, delta Kn minus of delta Jn, delta Kn times omega G, omega N, X alpha. This I can do a little bit more of manipulation and write it in the problem. Now look at the first term. It tells me that J should be equal to N because you have a delta JL and delta Kn. So it tells me that this expression will vanish unless J is equal to N and K equal to N. So then I can write this as, so I prefer to write this like this, omega J, omega N. This part I will not do any contraction, and this part, it becomes, so I'll do the summation, so it will become delta Kn times xk alpha times xn alpha. So it will vanish unless K equal to N. But what is xk alpha, xk alpha? Xk alpha times xk alpha, what is that? So I have delta Kn, xk alpha, xn alpha. What is this? Yes. What is this?
Xn alpha square.
Pardon?
Xn alpha square.
Yeah, it's going to be xk alpha times xk alpha. But this is nothing but R alpha square. Because it's x1 squared plus x2 squared plus x3 squared for the alpha part. So if you look at this part into this part, for this first term, it's nothing but R alpha squared. And then from here, if you look at this, what I'm going to get is delta Jn. So I will write this as xk alpha. And then I will write it as okay, so I will use, because K, this tells me delta K tells me that K should be equal to N. So wherever K comes, it should become N. So I will get it as omega N xn alpha. So this multiplied with this, I'm replacing K with L here. And then Jn will tell me that I can have to put omega J here and xk. Okay. Now you can see both the terms I have this omega J, omega L, so I can take it outside of the bracket. So let me take this outside of the bracket. And you can see that omega j, omega l doesn't have any, there's no summation over alpha here. So this summation over alpha is entirely over this part. But what is this term? Delta j l r alpha square. What is this? Delta JL R alpha whole square minus of XL alpha XJ alpha times M alpha. What is that? What is this quantity?
Moment of inertia.
This is nothing but your IJL for the alpha particle. If I'm summing over, then this whole thing is nothing but your. So therefore, what you find is that. So from here, what you can see is that what this tells me is that your kinetic energy is nothing but half mjl times energy. And this is something which people are familiar with. Which I could also further write it in the following way, that is mjl times omega l is nothing but your j. Okay, I will leave it because I don't want to use context. So it is nothing but your half Lj, because mjl times omega l is Lj. So your kinetic energy is nothing but, and that is precisely some things which you calculate, half I times omega, or this I omega square, or half L omega. Because the next expression I have written in terms of the angular moment. So here, if you, for example, if you're in the diagonal basis, then this is simply going to give you half I omega square. And further, what this also tells you, for example, here, you can see that this also tells you, because here now this is like the contraction of two vectors, it tells you that the kinetic energy must be a scalar. Or from here directly, if you look, it's a second rank tensor being contracted with two first rank tensors, so therefore the resultant must be a scalar. So, okay, I hope that this has at least shown you some of the, I mean, firstly, as I said, that by looking at the tensor and looking at the properties of that tensor, it means choosing basis properly, appropriately. Then in that case, what you can also see is that I think what I demonstrated earlier, one can actually look at this or get the symmetry properties in a very neat way. And further, I think I've also shown, I hope you have seen that the tensor analysis or the tensor algebra simplifies a lot of our future vector algebra and vector calculus. So I hope these two examples have demonstrated this. The other example which I earlier done was the electrical conductivity tensor calculation. Again, there we saw that by looking at the electrical conductivity tensor and by looking again there when we diagonalized, essentially what we did was we looked at the principal axis of that conductivity tensor, and from there I can demonstrate or I can figure out, given a particular material, whether it can conduct along a particular axis or not, or if it conducts, what will be its conduction, what will be the resistivity, and so on and so on. Now similar kind of applications are also there for magnetic susceptibility. Suppose you have magnetic material, then how much is it susceptible to the application of a magnetic field? Or in other words, how will the magnetic moment rotate with respect to the magnetic field? So that's another application of this tensor analysis. I give some of these when I make my problem sheet. I do a little bit more in tensors, that's why I make finding the problem sheet. Another very interesting application is of these ideas is, for example, when you want to see, I told you the moment of inertia will tell you about the shape of a rigid body. So, for example, it will tell you whether it is spherical symmetry, whether it has, or whether it has cylindrical symmetry, and so on. I'll just mention another thing. So if you look at this quantity, see basically that moment of inertia tensor had this form. This was the main part. Have you seen such an expression anywhere else? Have you encountered this anywhere else? Okay, in electrodynamics, you people have studied multiple expansion of potentials.
Yes, ma'am.
So, did you encounter any such kind of an object when you did such a multiple expansion? Okay, when you do the multiple expansion for a potential or some arbitrary charge distribution, what are the terms which you will get there for the potential? What is the first term corresponding to? See, what do you do there? You have a arbitrary charge distribution, and then you are trying to find out the potential distribution. And then what you do is you assume now that you are looking at the potential at a point very far away from that charge distribution, and you expand that potential in terms of what are known as force, which is moments actually. So, what is the zeroth order? What is the first term in that expansion? What does that correspond? So imagine that I have some arbitrary charge distribution. I'm looking at it very, very far away. So what should be the potential due to this charge distribution? Suppose the charge is Q, total charge on the system is Q. What should you expect answer? Okay, forget about charge distribution. Suppose I have a point charge kept at the origin. And what is the potential due to a point charge?
1 by R.
Pardon?
1
Yes.
by R.
Yeah, up to 5. It's not just 1 by R, it will be Q by R, no? And if you're in SI units, you'll get this 4 pi
Goes
epsilon.
as 1 by R. Yeah.
Yeah, Q is also required because it is going to be proportional to the total charge of the body divided by the distance or the location of the point where you're making the position observation. Right, and the total charge there will be Q. Okay. Now suppose it's not a point charge, but I'm assuming that it's some extended object, but with the total charge Q. So when I'm looking at this very, very far away. So the first term in that expansion for your V will be like still a Q by R if you go and see it. That is n equal to 0 term. What will be the next term?
Dipole term.
It's a dipole term because you find that if we have the potential will be like a 1 by R cube. Then after that, what will you get? Or actually 1 by R square because the force will become the 1.
Quadruple term.
Then you will get a quadruple term. That is the n equal to 2 term. Okay, and if you look, you must have done this expansion, and if you remember that expansion, it comes in terms of this Legendre polynomials. The first one will be P0, which is 1. So you'll get this 1 by R to the power of n multiplied by Pn of R prime dot R, where R prime is a vector inside the charge distribution. So the first term will be P0, that is the first Legendre polynomial of order 0. Then you will get P1, that dipole moment will give you that. So you'll get a cos theta there. That's why you will get. So that's why for a dipole moment, it will depend upon the direction in which I'm seeing. And then if you look at the next term, n equal to 2 term, you will get the P2, the Legendre polynomial. That's P n equal to 2, which is really like 3 cos square theta minus 1 with some half factor, I think, to all numbers. And the cos theta there is the angle between your observation, the vector at which you're doing the observation. So it's like suppose I'm here. So if this is my body, and let's say I'm making the observation here. So this is your R, and so this is like R prime Z, and this is R. So this is inside the charge distribution. You're doing the integral over dq R prime. So this angle is theta here. So you will find that you will get a 3 cos square theta. So this cos theta you can actually write in terms of R prime dot R. Because if I take the unit vectors. And all right. So I will give this as an exercise. Show that particular term can be written in this form. So this actually will be, because you will get an r prime dot r cos square theta will come, so you will get an r prime dot r and r prime dot r, so it will become like this multiplied by this, and most generally we can write this term in this form multiplied by some factors. So your quadrupole moment will actually have this kind of an expression. Okay, now let me ask you something. Now, if you had, suppose you didn't have a dipole moment, and let's assume that, again, go back to your charge distribution, and let's say that I get nothing else except just the first term. What will it tell you about the shape of your system, of your charge distribution?
That it is a point charge.
Spherically symmetric.
You have
Spherical.
exactly spherical symmetry. Okay, it will be like that. On the other hand, if you had, suppose I will tell you the dipole moment is zero, but I don't have, I still have a quadrupole moment, then what will it tell you about the shape of that charge?
Cylindrical symmetry.
No.
Uh,
So when should I expect? Suppose I'm telling you now I have a charged body whose dipole moment, I'm going to get a dipole moment. If I look at that in multiple expansion, I'll always get a dipole moment of zero, but I still will have a quadrupole. What can I say for that? It's not cylindrical symmetry. Okay, it will tell you that the shape can it be now purely properly spherically symmetric? It cannot be. What you will find is that there may be bulges now, either around the equator or around this side. So you can have oblate, prolate. Okay. And in fact, now I'm going to tell you that you can do the same thing. This kind of multiple expansion you can also do for an extended massive object. So, for example, if I have, say, let's say I have some mass distribution, okay, and then I have another mass here, and then I ask that. So to think of this as a test mass. Okay. Then I ask what is the potential which this test mass is going to see because of this mass distribution. Now this is the mass distribution. Okay. If this was a point mass, what should have been the gravitational? Obviously, there's going to be a gravitational potential. What should be the gravitational potential? If both the bodies, what will be the potential which will be seen at this point because of this? Let's say the distance is r.
MGR.
Well, minus, it's an attractive potential, -1 with a capital T. Okay. Now, if you have an extended mass distribution, exactly like the way you get in your electrodynamics, where you had this multipole expansion, I can do a similar kind of a multipole expansion for this gravitational potential as well. And again, what you will find is that you won't get a dipole because now the mass is only of one kind. Electrodynamics will get a dipole because I get both plus E and minus E. Here you will not get a dipole term, but you can get quadrupole terms. And that will tell you that your mass or your object, this mass is not a spherically symmetric mass distribution. And now if I say that, for example, let's consider this to be our Earth, and this is the Sun. Okay. And we know that our Earth is not fully spherically symmetric. There are bulges at the equator. Okay, so you get this extra quadrupole moment in the gravitational potential, and in fact that leads to your precession of the equinoxes, or your, see, the axis around which the Earth is rotating, and the Earth is also rotating. That axis itself twists because of this. And if you wish to find out how it is twisting, that you can again use all your moment of inertia language. And similarly, this kind of things can also you will find that similar considerations will also apply. Now we have artificial satellites which are orbiting around the Earth. So those orbits also will see I would have expected full spherical orbit, but because of the fact that your Earth is not a completely spherically symmetric object, but it has these equatorial bulges, you will find that that orbit also will precess. And again, those precisions of these satellite orbits can be found out using this tensor analysis of moments of inertia. So they are really very interesting applications, but I won't go into those. So I'll stop here, and tomorrow we'll continue at the same time at 11:15. Okay, thank you. Where do I go?
Did they have other lectures?
Huh?
How many more lectures?
Okay, I need to take because for second year,